All right, with linear spaces behind us, at least the definition's set up, let's consider linear operators. So we'll define the most fundamental object of functional analysis, the linear operator. The rest of the course is devoted to properties of linear operators, classifying linear operators, mappings from a linear space to the real numbers or examples of linear operators, but more specifically, they're examples of functionals. And the title of the class is Functional Analysis. So big time linear operators fit in the discussion. So we'll set up some general definitions in this section and kind of chat about how you've seen a lot of this stuff before and you saw it in sophomore linear algebra. So first definition, if X and Z are two linear spaces over the same scalar field, a linear operator from X to Z is a rule, capital T, that associates with each lowercase x and x, so each vector in set X, a unique element, T of X in Z. It's an element of Z, so that's a vector as well, such that for all vectors, lowercase x and lowercase y, in linear space capital X, and for all scalars alpha, we have two things holding. T of x plus y equals T of x plus T of y, and T of alpha x equals alpha T of x. So these linear transformations behave in a desirable way in terms of their interaction with vector addition. We could maybe word this something along the lines of vector addition is preserved by linear transformations. Here, inside the linear transformation, we have a sum of two vectors in linear space capital X. Here, we also have a sum of two vectors, but it's in a different place. Here, the vector sum is in linear space capital Z because T of X and T of Z, T of X and T of Y live in the space capital Z. And here we have, in some sense, a preservation of scalar multiplication. T of alpha X equals alpha T of X. So here on the left-hand side, alpha X, of course, that's scalar multiplication, but that's scalar multiplication in linear space X. And on the right-hand side, we've got alpha times a vector as well, but that vector lives in linear space Z. So that's scalar multiplication in linear space Z. So kind of informally, what a linear transformation does is it preserves vector addition and it preserves scalar multiplication. Combine those two and it preserves, as we'll say down here, it preserves linear combinations. That's why they're called linear transformations or linear operators. So we've formally defined these as linear operators. They're also called linear transformations. I'll probably use that term again and again. That's what they're usually called in sophomore linear algebra, or maybe linear mappings. Linear operators, linear transformations, I'll stick mostly with that terminology. And yes, if we combine these two properties, transformation of the sum is the sum of the transformations and the interaction with scalar multiplication. If we were to apply linear transformation, linear operator, capital T, to a linear combination, alpha X plus beta Y, that would be a linear combination in linear space capital X, then we get a linear combination on the right-hand side of the images, alpha T of X plus beta T of Y. That's a linear combination with scalars alpha and beta and the vectors coming from linear space capital Z. So, in a sense, linear transformations preserve linear combinations, and that's why they're called linear transformations or linear operators. And as promised, let's talk about where you've seen this before. You've seen it in linear algebra. When we were looking at linear operators, we certainly did call them linear transformations there, from Rn to Rm. A linear transformation from Rn to Rm is equivalent to an m by n matrix. See, I guess, Theorem 3.10, matrix representations of linear transformations. Some link to some notes from linear algebra there. Yeah, every linear transformation determines a linear, every matrix of appropriate size determines a linear transformation, and every linear transformation between these two sets determines a matrix. This is about that matrix determined by the linear transformation. It's computed by applying the transformation to basis elements. So you've seen this idea of a linear operator or linear transformation before, and they were related to matrices before in the linear algebra setting. The null space or kernel of a linear operator, capital T, denoted capital N of capital T, is a set of all x vectors in linear space capital X such that T of X equals 0. All right, the word kernel is a word in linear algebra associated with linear transformations. Maybe null space was a term associated with matrices. Well, matrices, linear transformations, it's the same thing when we're in the appropriate setting. This term kernel, possibly you speak of kernels of homomorphisms in a modern algebra class. And in fact, you relate one-to-oneness and the kernel of a homomorphism in a modern algebra class. Well, we're about to do the same thing in here. Continuing the definition, the range of T, also called the image of X under T, I'll probably stick with the term range, denoted R of T, is the set of all Z vectors in linear space capital Z, such that T of X equals that vector Z for some vector X in linear space X. A little comment about the notation. So we've written T maps X into Z, and that's a proper way to read that. And here we're doing it in the setting of linear operators. You may see F as a function mapping the reals into something else. Whenever you write a function mapping one place into another, one set into another, about as general as we can make it, it's understood that this is the domain. So T is defined on all of vector space X. The domain is that first set that you write there. The second set over here, that's not the range. That's where the range lives. So sometimes it's called a codomain. That's a term commonly used in linear algebra. What the codomain tells you is the kinds of things you get out of a function. I might put numbers in and get sets out, or put numbers in and get vectors out, or put vectors in and get numbers out. The kind of thing that comes out is told by what's written over here. By writing this, we know this transformation T takes in vectors from set X and gives out vectors that live in set Z, linear space Z. And it's got some additional algebraic properties given by the definition of linear upstairs. So the range is the stuff that comes out of the transformation when you allow the input to range over. T of X ranges over all of linear space capital X. And the range is a subset of this linear space. Well, we might be interested in when the range is this set on the right-hand side. And that leads us to the definitions. A linear operator T mapping X to Z is surjective or onto if R of T equals Z. That is, the range of T actually equals all of this set over here. So you plug in all vectors X from linear space capital X into this, apply transformation T to all those vectors, and you'll get everything in Z. It maps onto Z. Surjective is more of an algebraist term. Analysts more prone to use the term onto. Your senior level analysis class and your graduate level analysis class. You probably talk more about one-to-one and onto than you did surjective and injective. Your graduate algebra class or your senior level algebra class, you probably taught more surjective and injective than you did one-to-one and onto. Anyhow, surjective or onto, I'll use those somewhat interchangeably. I lean towards onto, given more of an analysis background than an algebra background. But it's onto if the range equals all of this codomain up here. It's injective or one-to-one if t of x equals t of y implies x equals y. The only time you get the same output is when you have the same input. You might read it like that in terms of this type of mapping. And if a mapping is both surjective and injective, that is both onto and one-to-one, then it's called a bijection. I mean, that's common terminology, more so than this surjection, injection terminology. Bijections was used in lots of places. But anyhow, we might be interested in one-to-one and onto transformations before we're done. In linear algebra, we show that a linear transformation between two vector spaces is injective, that is one-to-one, if and only if the kernel of that transformation consists only of the zero vector. See corollary 3.4.a. This is my numbering scheme from Fraley and Beauregard's linear algebra book, one-to-one and kernel. So the same kind of thing holds here. We're dealing with linear transformations in this section of linear algebra, possibly not dealing with the matrix representations of them yet. Of course, dealing with linear transformations in the appropriate setting is equivalent to dealing with matrices, especially if we have linear spaces Rn and Rm. Then we're definitely dealing with matrices. And then we could talk the null space of a matrix versus the kernel of a linear transformation. It's the same thing in that setting. And our first theorem says linear operator T mapping linear space X to linear space Z is injective if and only if the null space of T equals 0. A little comment about this notation. This is how the book presents it. That is to say, the only thing in the null space is the 0 vector. That would be a vector, right? We're taking the things mapped to the 0 vector by that transformation. So that's the set consisting only of the 0 vector. By the way, which 0 vector is that? It's the one that lives here. Remember, the null space is the set of all vectors in X that are mapped by T to the 0 vector. So that 0 vector, that actually lives in Z, where X itself lives in X. This is a 0 vector in Z. The null space of T as the vectors in X that are mapped by T to the 0 vector in Z. So it's clear from context. Yeah, well, you can decipher it from the context. But strictly speaking, 0 here represents 3 possible things: the 0 vector in X, the 0 vector in Z, and the 0 scalar. But we can figure it out from the context. Let's look at a proof of that. It's straightforward. So we'll go to the online notes. That contains proofs and a handful of examples. And let's establish this. Injective, that is one-to-one, if and only if the null space of T consists only of the 0 vector. Well, suppose the null space of T does consist of the 0 vector, and suppose T of X equals T of Y. To show injective, to show one-to-one, we need to show X equals Y. T of X equals T of Y implies X equals Y. Definition of injective, and we get this little hypothesis here in this case. All right, well, 0 vector equals T of X minus T of Y. Subtract T of Y from both sides, you're left with a 0 vector. By the way, it's a 0 vector in space Z. Linearity here allows us to rewrite T of X minus T of Y as T of X minus Y. Quick comment. It's not any sort of distribution. Distribution applies when you have something like multiplication. This ain't multiplication. This is linearity of a transformation that allows us to rewrite this quantity as that quantity. It isn't factoring the t out or anything like that. It's the linearity of the transformation. So t being linear, we can rewrite things like this. But then you've got something here, x minus y, mapped under t to 0. Then that something there, x minus y, must be in the null space of t. Well, we said the only thing in the null space of t was a 0 vector. So that thing there, x minus y, must equal the 0 vector, or x must equal y. That's what injective is. We assume t of x equals t of y, and we showed x equals y. That is injective. That is one-to-one. So it must be, in this case, t is injective, is claimed. If the null space consists only of the 0 vector, then t is injective. Let's reverse it, converse. Suppose t is injective, that is t of x equals t of y, requires x to equal y. And let's see what's in the null space. You know t of 0 equals 0. Linear transformations always map the 0 vector to the 0 vector. Easy enough, show it by considering t of 0 plus 0. Use the linearity and you'll draw this conclusion. So if we take z to be something in the null space of t, then t of z must be 0. That's what that means. T of z equals 0, but t of 0 also equals 0. So we've got t of z equals t of 0. Well, that implies z equals 0 under a hypothesis of one-to-oneness, under a hypothesis of injective. So we've assumed z is in the null space of t and concluded z must be the 0 vector. So the only thing in the null space of t is the 0 vector, and that was the converse of the first claim. So injective linear transformation, if and only if null space consists only of the 0 vector. Returning to the notes, let's consider, we're working our way into defining an inverse transformation here. Let's consider kind of an equation. Suppose t maps x to z, linear spaces, is a linear operator. Consider the equation tx equals z. X and z from the obvious places. Does that have a solution? Well, a solution, x, exists for all z vectors in capital Z, if and only if the range of t is all of z. If the range of t equals all of z, then there's an x, a vector x, such that t of x equals z for all z in the codomain. So we get a solution for all z only when the range of t equals all of z. So if a solution exists for all of z, then it's unique provided the null space of t equals 0. Which means, as we just saw from the previous result, t of x equals t of y if and only if x minus y is in the null space. So if we have a solution to that equation, t of x equals z, suppose x and y are both solutions, then t of x and t of y are equal because they both equal z. But then that occurs if and only if x minus y is in the nullity. Actually, I guess we saw in the proof of that theorem. But we get those to be the same under the conditions that the null space equals 0. So we can associate this null space consisting only of the 0 vector, which really means one-to-oneness. We can associate that with unique solutions to these kinds of equations. So if we have the null space equals 0, and we had the range of t equals all of z, we'd be totally in business to define an inverse transformation. All right, so we got a definition here. It's not exactly that. We're taking the range simply as the range, but we're assuming we have n of t equals 0, null space of linear transformation t consists only of the 0 vector. Good news, that means you got a one-to-one, an injective linear transformation. then we can define the inverse transformation, mapping, well, whatever that's onto. It's onto its range. The range may not include all of z, but it's onto its range for sure. So we can define T inverse mapping the range back to x as T inverse of z equals x, where we have the equation Tx equals z. We've got Tx equals z has a unique solution, x under these conditions described above. We've got the one-to-oneness that allows us to draw that conclusion. We've got some onto-ness, some surge activity as well when we consider the range as the output. So this parameter x is uniquely defined by the previous paragraph. So there's conditions under which we can talk about inverse transformations. Next result says, if T maps x to z is linear with null space equals 0, that means T inverse exists, at least defined on the range of T. T inverse mapping the range of T into X is also linear. So basically what this says, if T is linear, then under appropriate conditions for T inverse to exist, T inverse is also linear. Let's look at a proof of that. Okay, it's just one slide. So we're trying to show T inverse is linear. This can't be that hard. All we know is the definition of T inverse. And we're good to go on the existence of that mapping, given that the null space of T equals 0. So let Z1 and Z2 be in the range of T. That's the domain of the T inverse function. Say Z1 equals T of X1 and Z2 equals T of X2. And that's how they got to be in the range, is by equaling the image under T of something in X, say X1 and X2 are respectively. And take yourself a couple of scalars, call them alpha and beta. Alpha Z1 then is alpha times T of X1 because Z1 equals T of X1. I can take that alpha and put it inside that transformation because it's a linear transformation. Similarly, beta Z2, beta being the scalar we introduced. Hey, Z2 equals T of X2. So I can make that substitution. T is still linear. I can put the beta inside, part of the definition of a linear. So we've got alpha Z1 expressed like this, beta Z2 expressed like that. So if we look at alpha Z1 plus beta Z2, substitute in alpha Z1, we've written as T of alpha of X1. Beta Z2, we've written as T of beta X2. Linearity of T, again, allows us to take the transformation of the sum and write it as a sum of transformations. But I'm using linearity here. Again, don't give me nothing about factoring or distribution. It's linearity that gives this property here. So now we've got T of a linear combination here. T of this equals that. And we define the inverse mapping as when T of this equals that, T inverse of that equals this. In other words, T of this element of linear space capital X equals this element of linear space capital Z. By definition, T inverse of this element of capital Z equals this element of capital X, linear space. Linear space is Z and X. That is, T inverse of alpha Z1 plus beta Z2 equals alpha X1 plus beta X2. Looking at these outer two quantities and the definition of T inverse. Hey, alpha X1, we were just talking about alpha X1. That would be alpha T inverse of Z1 from this statement here. If Z1 equals T of X1, and T inverse is defined, then T inverse of Z1 equals X. Don't think of it as composing somehow, maybe taking T inverse of both sides. It's straight up the definition of T inverse. It's even easier. So T inverse of Z1 equals X1. We'll make that substitution. Here's X2. Similarly, T inverse of Z2 equals X2. Make that substitution. And that gives us this. it looks like we're done. So T inverse is linear. So how do you show a transformation as linear? You show it preserves linear combinations. So we're trying to show T inverse is linear. So we need to show T inverse of a linear combination is a linear combination of the T inverses, if you will. And that's exactly what we've got. T inverse of this linear combination of elements of linear space capital Z equals a linear combination of the inverse images. That's exactly what you need to show linear transformation T inverse is linear. Apply it to linear combination, get a linear combination of applications of it. Very definition of linear. Back to the notes, that's the last little proof. We do have a little computational argument here as well to justify the next definition. Let X and Z be linear spaces. If T1 and T2 are linear transformations to X sub Z, then for any scalars, alpha and beta, we can define the transformation alpha T1 plus beta T2, also mapping X to Z, and defined as alpha T1 plus beta T2. So there's the transformation. We're applying it to vector X in linear space capital X, and we're getting out, by definition, alpha T1 of X plus beta T2 of X. So there's the definition of the sum of two linear transformations. So where we stand now is not only having vector sums defined and scalar sums, but also having sums of linear transformations defined as given there. What we're going to show is the linear combination itself, the highlighted thing there, is in fact a linear transformation. So take gamma and delta as scalars, X and Y, vectors in linear space capital X. We want to show this highlighted thing is linear. So what we want to show is this highlighted thing applied to a linear combination equals gamma of the highlighted thing applied to X1 plus delta highlighted thing applied to X2. We want to show the highlighted thing of a linear combination as a linear combination of the highlighted things. That's how we show the highlighted thing is linear, definition of linear. It's a little muddled up because we've got linear combinations of linear transformations and linear combinations of vectors. But look what we've done in the first line. We'll go through the computation, but we're taking the highlighted thing and applying it to this linear combination. And when we're done, we're getting out gamma times the highlighted thing applied to X1 plus delta times the highlighted thing applied to X2. And that's exactly how we've been dealing with the definition of linearity and the couple of little times that we've used that definition. So drawing this conclusion will show that the linear combination of linear transformations is itself a linear transformation. It preserves linear combinations. The linear combination we're preserving is gamma X1 plus delta X2. So we'll apply that transformation, alpha T1 plus beta T2, that thing, apply it to the linear combination of vectors. Gamma X1 plus delta X2. Okay, that's a linear combination of vectors in linear space capital X, the domain. Definition says what we'll get is alpha times the first linear transformation applied to the vector. So the vector X is being replaced by this linear combination of vectors here. So substitute for X, this thing in the definition. So that'll give us alpha T1, that thing, plus beta T2, that thing. Alpha T1, that thing, the linear combination of vectors, plus beta T2, that thing, the linear combinations of vectors in linear space capital X. Very definition of the linear combination of these two linear transformations is given right there. Okay, I think we're probably done with that definition. Now let's use properties. T1 and T2 are both linear, so you know what's going to happen there. All right, so let's take T1, apply it to this linear combination. We're going to do this one little step at a time. First, let's break that sum up Right, we've got T1 of a sum of two vectors. That'd be the sum of T1 of the first and T1 of the second. So we get T1 gamma x1 plus T1 delta x2. Definition of linearity, T1 is linear. And the same thing with the T2 transformation. It's also linear. We've got an alpha out front of the T1s and a beta out front of the T2s. Notice the parentheses, the books are balanced. T2 of gamma x1, T2 of delta x2. All right, we could also bring these gammas and deltas outside of those transformations. We will, just not in the next step. Next step, let's take the alpha and distribute it, and take the beta and distribute it. So we'll get an alpha on this vector and this vector, and we'll get a beta on this vector and this vector. Simple distribution, scalar multiplication over vector addition. Now let's bring those scalars out. T1 is linear, so we can bring the gamma out here and the delta out here. T2 is linear, we can bring the gamma out here and the delta out here. So we've done exactly that. Alpha, delta, alpha, gamma, alpha, delta, beta, gamma, beta, delta. Linearity, two properties of a linear transformation. You can break it up over vector sums and you can bring scalars out. Definition of that. Okay, let's do just a little arithmetic here. Move these things around. We've got a gamma here and a gamma here. I can only highlight one thing at a time. Let's collect those terms together. These two terms involving gammas, let's collect those together. And these two terms involving deltas, let's collect those together. So we'll factor gamma out of this and this. Get the gamma up front, you'll be left with alpha T1 of x1, right? And beta T2 of x1, beta T2 of x1. Factor delta out here, you'll be left with alpha T1 of x2, right? Delta out here, beta T2 of x2, right? So all we did was factor gammas and deltas out from those vectors. Hey, here you've got alpha T1 of x1 plus beta T2 of x1. By definition, that's alpha of T1 plus beta of T2 of x1. This is by definition that linear combination of transformations applied to x1. Let's scroll up. Right. That's exactly the definition we got here, except it's got x sub 1s instead of x itself. So to have alpha T1 of something plus beta T2 of the same thing is to have the linear combination of those linear transformations applied to the input. Well, that's exactly what we have. That is alpha T1 of x1 plus beta T2 of x1. That's the linear combination applied to x1. Guess what? Same thing over here. This is the linear combination applied to x2. The linear combination applied to x2. So what we've shown is take this transformation, apply it to the linear combination, gamma x1 plus delta x2, and get out a linear combination of this as applied to x1 and x2 as given. That's the very definition of linear. So a linear combination of linear operators is itself linear. Linear, linear, linear. You know, lots of stuff about linear things. Nonlinear is a different story. So for linear spaces x and y, the linear space of all linear operators is itself a linear space. Linear combinations of linear transformations are themselves linear. So we could make a linear space out of the linear transformations. Sounds a bit weird, but we're going to do a lot of this. So define this linear space of linear transformations as given there. Calligraphy L of x comma z. If we were dealing with a setting of Rn and Rm, that linear space would be made up of m by n matrices. So you've seen this kind of thing before. Can you take linear combinations of m by n matrices as if they were vectors? Of course you can. M by N matrices, they form a vector space as well. You can add them together and scalar multiplication stuff. Yeah, you actually have a vector space of M by N matrices. That is, you have a linear space of M by N matrices. That's all we did here. So we have a linear space of linear operators or linear transformations. Same thing. And a quick little comment, were we to map X to itself, if we took linear transformations from X to itself, the notation is abbreviated a little bit, just as L of X. It's all linear operators that map X to itself. Very consistent with things you saw in sophomore linear algebra, linear transformations of Euclidean spaces. Yeah, they were represented by matrices. And if I take the collection of all M by N matrices, you know, that's a vector space of M times N. In fact, it's isomorphic to R to the Mn if the scalars are real. That is the vector space of M by N matrices with real scalars. So it turns out this itself is a linear space, as we just observed. And that takes care of our intro to linear operators. Next video will be pretty brief. We'll finish up chapter 1, and then in chapter 2, we'll get down to real business. So have a nice day. I'll see you in the next section.